Greetings from NYU. Today was my first day of Honors Algebra 1, and today we're going to be talking about groups. Everyone knows what a function is, a regular function like f of x equals x squared. We're not in the regular Algebra 1, of course, we're in modern Algebra 1. Instead, we're not going to be talking about functions that go from a real number to a real number, like this one right here could go from example rad2 to 2. Instead, we're going to be talking about something completely different. Well, not completely different, but we're going to be talking about functions that go from one set to the other. These don't have to be the real numbers. They could be integers, rational numbers, they could even be finite sets. All that matters is that there's a relation between one and the other. And this is where we get to how we can relate between two sets. Like, for example, if we have 1, 2, 3, and 4, 5, 6, there are tons of different ways that we could create a relation between them. I mean, the simplest way to think about it is a one-to-one relationship. How many ways can we make a one-to-one relationship? Well, there are three different ways there are three different values we could pick for f of 1. Once we pick the value for that, there are two different values we can pick for f of 2. Once we pick the value for that, there's only one choice left for f of 3. So that means it's 3 times 2 times 1, or 3 factorial, which is equal to 6 different ways. And these 6 different functions all form part of a group. But now, back to this function. We mentioned that this is just one-to-one. Like, for example, 1 might be to 5, 2 might be to 4, 3 might be to 6. So this is what we call a bijective relation. But we can also have relationships that are injective and surjective. What do those mean? Well, let's take an example of injective. Something is injective if not all of the points are used. Like, for example, what can I think of? Like, for example, y equals 1 over x.
It doesn't exist.
Yes. So, the input, the domain, is r without 0. And the output is r. Well, I mean, the codomain, or the range, they're the same in this context, is r. So essentially, what this means is that some parts of the domain don't have outputs. All right. So now, what about surjective? Well, what that means is that some parts of the range don't have, or some parts of the codomain rather, don't have unique inputs. So, for example, take y equals x squared. The codomain is r, all of r. But the range is only the positive integers, plus, of course, 0. So, of course, once we graph it, you can see every single number on the number line maps to its square. But no square, none of the outputs, no part of the range is in the negative numbers. There we go. So that's what injective and surjective basically means. And you can remember it even easier if we're dealing with finite sets, which we won't often be dealing with. But if it's injective, that means that the magnitude or the cardinality of the domain is less than the cardinality of the codomain, less than or equal to. That's an important part. If it's surjective, that means the cardinality of the domain is greater than or equal to the cardinality of the range. And of course, when we combine them, we get that their cardinalities are equal. Or in other words, there's a one-to-one correspondence. Every input has a unique output, and every output has a unique input. Like y equals x, or any other odd function, like for example, x cubed. You can see there are negative cubes and every single number has a cube. So it's very obvious to us, this graph is not undefined anywhere, that this has to be a bijective function. And what does it mean if we're bijective? Well, obviously, if we know that f of a is equal to b, and there's no other value we can put in to get b back, then the inverse function also exists. We can also have f minus 1 of b is equal to a. But for example, if f of a is equal to b and f of a is also equal to c, which would make this an injective function, then that means, if f of a is b, but f of c is also b, which would make this an injective function, then f minus 1 of b could be a or c. We don't know which one is it supposed to be. So then that means that for something that is solely injective and not surjective, this does not exist, and vice versa. So that is, oh, right, and I guess I'll show an example of surjective too, but it should be way more obvious. Because, of course, when it's surjective, that means not all of the codomain is used. So, for example, well, y equals x squared, the example you offered, has an easy inverse. Y equals root x, right? But here's the problem. The thing is, y equals x squared works, it exists as a function because there's no actual hole. I mean, in 1 over x there is a hole, but what I mean is there's no large region where it's totally undefined. This works as a complete function because f of minus 1 exists and f of 1 exists. Oh my god. But the other chalk is green. And f of 1 exists. So, however, f minus 1 of 1, if we're talking about x squared, is obviously 1, because 1 squared is 1. F minus 1 of minus 1, what are you going to write? I? So, instead, that's how you know that neither injective or surjective functions alone have inverses. They have to be combined into a bijective function to have an inverse. All right. So now, finally, let's get to the topic of groups. Groups are kind of like sets, except for one crucial thing. Groups are sets that have operations associated with them. And an abelian group, which we'll be studying very specifically, is closed under that specific operation. So what's an example of the group? Well, for example, we could have the group of all possible rotations in 3 dimensions, which we call SO3. Or we could go simpler. We could have R. And an operation we could have over here is we can add 2 rotations, we can also subtract them. And the key thing about this is that it also has to have an inverse to this. So if we have, for example, the integers under multiplication, there's no inverse to multiplication that works solely within the integers. Like 1 over 4 isn't an integer, is it? So that means that this is not a group under multiplication. Got to make it something like addition or subtraction for it to work. And in a similar way, you can't really do anything with the real numbers. Well, we can actually. The square root doesn't work as a group because taking the square root of a negative real number will give you something not in the real numbers. So, an abelian group is something, oh wait, sorry, squaring something in the real numbers doesn't work because the multiplicative inverse doesn't always, wait, never mind, okay. So there's not really an operation in the real numbers you can use. But an abelian group is very specific in that something has to be closed under not only its inverse, the inverse not only has to exist, but this also has to be closed under its operation. Like, for example, the integers are closed under addition. Good. The integers are not closed under division. Bad. The reals are closed under squaring, or multiplying, or dividing. Good. But the real numbers aren't closed under square rooting. Bad. So this can keep going on and on and on. So that's the basic rundown of functions and groups. Thank you everybody for watching, and I'll see you in the next one. Alright, so these are functions in groups. So a function, as you know, can be the regular function from reals to reals, but they can also just be a function between any two general sets. They could even be finite sets. Now, a one-to-one correspondence, where one element of the input goes to one element of the output, is called what we call bijective. Now, an inverse of a bijective function exists, and that's what's so special about this. For example, this isn't bijective because there's no number in the domain that corresponds to a negative real number. So that means that the codomain isn't fully filled by the domain. So what about groups? Well, we can have the group of rotations or just a regular group like the regular set like the real numbers, but they also have to be associated with an operation. For example, addition. If we're talking about a group of functions, the operation could be composition.